The Big Bang is the definitive narrative of modern cosmology, a bold declaration that our universe had a beginning and has a finite age, just as the humans who live within it. That finite age, in turn, is defined by the evidence that the universe is expanding. Those two ideas, a singular cosmic beginning, followed by billions of years of cosmic growth, are so strange that some people have never made peace with them. As a result, skeptics have been questioning the validity of the Big Bang model for as long as there has been a Big Bang model. Among mainstream cosmologists, doubts about the Big Bang largely melted away in the 1960s with the discovery of the cosmic microwave background, an omnidirectional buzz of radiation that makes sense only as a relic from the hot, early era of the universe. But around the fringe, the doubts have persisted. Lately they have intensified, inspired by groundbreaking discoveries made by the James Webb Space Telescope in the early universe. In a stunning observation, NASA's time machine, the JWST, has just detected unimaginable massive galaxies at the edge of the observable universe, challenging the Big Bang, our supreme theory about the origin of the universe. Is it time we must completely change our view of the cosmos and our own existence? The answer will be revealed in today's episode of Eyes 200M. The idea for the Big Bang first came about back in the 1920s and 1930s. When we looked out at distant galaxies, we discovered something peculiar. The farther away from us they were, the faster they appeared to be receding from us. According to the predictions of Albert Einstein's general relativity, a static universe would be gravitationally unstable. Everything needed to either be moving away from one another or collapsing towards one another if the fabric of space obeyed his laws. The observation of this apparent recession taught us that the universe was expanding today, and if things are getting farther apart as time goes on, it means they were closer together in the distant past. An expanding universe doesn't just mean that things are getting farther apart as time goes on, it also means that the light existing in the universe stretches in wavelength as we travel forward in time. Since wavelength determines energy, shorter is more energetic, that means the universe cools as we age, and hence things were hotter in the past. Extrapolate this back far enough, and you'll come to a time where everything was so hot that not even neutral atoms could form. If this picture were correct, we should see a leftover glow of radiation today, in all directions, that had cooled to just a few degrees above absolute zero. The discovery of this cosmic microwave background in 1964 by Arno Penzias and Bob Wilson was a breathtaking confirmation of the Big Bang. It's tempting, therefore, to keep extrapolating backwards in time to when the universe was even hotter, denser, and more compact. If you continue to go back, you'll find a time where it was too hot to form atomic nuclei, where the radiation was so hot that any bound protons and neutrons would be blasted apart, a time where matter and antimatter pairs could spontaneously form, as the universe is so energetic that pairs of particles and antiparticles can spontaneously be created, a time where individual protons and neutrons break down into a quark-gluon plasma as the temperatures and densities are so high that the universe becomes denser than the inside of an atomic nucleus. And finally, a time where the density and temperature rise to infinite values, as all the matter and energy in the universe are contained within a single point, a singularity. This very final point, this singularity that represents where the laws of physics break down, also is understood to represent the origin of space and time. And this was the ultimate idea of the Big Bang. Of course, everything except the last point has been confirmed to be true. We've created quark-gluon plasma in the lab. We've created matter-antimatter pairs. We've even done the calculations for which light elements should form and in what abundances during the early stages of the universe are. and we've made measurements and found that they match with the Big Bang's prediction. Coming forward even further, we've measured the fluctuations in the cosmic microwave background and seen how gravitationally bound structures like stars and galaxies form and grow. Everywhere we look, we find a tremendous agreement between theory and observation. The Big Bang looks like a winner. But the universe as we see it has some properties and some puzzles that the Big Bang doesn't quite explain. If everything began from a singular point, a finite amount of time ago, you'd expect different regions of space would have different temperatures, since they wouldn't have had the ability to communicate and exchange particles, radiation, and other forms of information. Leftover particles, relics from the earliest, hottest times, such as magnetic monopoles and other topological defects, and some degree of spatial curvature, since a Big Bang that arises from a singularity has no way to balance the initial expansion rate and the total matter and energy density so perfectly. But none of these things are true. The universe has the same temperature properties everywhere, no leftover high-energy relics, and is perfectly spatially flat in all directions. Either the universe was simply born with these properties for no foreseeable reason at all, or there is a scientific explanation, a mechanism that caused the universe to come into existence with these properties already in place. On December 7, 1979, physicist Alan Guth had a spectacular realization, an early period of exponential expansion that preceded the Big Bang. What we now know as cosmic inflation could have caused the universe to be born with all of these specific properties. When inflation came to an end, that transition should then give rise to the hot Big Bang. Of course, you can't just build an extra idea into your old theory and declare that your new one is better. In science, the burden of proof on the new theory is much more severe. As a result, the doubts have persisted. And lately, they have intensified, inspired by groundbreaking discoveries made by the James Webb Space Telescope in the early universe. In just its first year of scientific operations, the $10 billion U.S. infrared telescope has delivered stunning views of the nascent universe, finding large numbers of surprisingly bright galaxies that existed at a time when the cosmos was in its infancy. With its 6.5-meter mirror, JWST was designed to investigate this early era, which was mostly out of reach for its predecessor, the 2.4-meter Hubble Space Telescope, or HST. Observations thus far from the JWST have simply astonished researchers and left them trying to digest exactly what they were seeing. According to the standard model of cosmology, after the fiery Big Bang, some 13.8 billion years ago, the universe cooled and energy turned into matter that eventually coalesced during the first few 100 million years, forming the first generation of stars and galaxies. Astronomers thought they had a decent understanding of this process. But JWST's initial results may suggest that stars and galaxies were forming far faster than anyone expected. The telescope had done nothing less, read the headlines, than break the universe and upended models of cosmic history. Subsequent data from the JWST have ruled out some of the more dramatic findings, and new simulations can accommodate at least a few of the strange observations. But some bright, massive, and early galaxies continue to confound theorists, suggesting that our understanding could shift in the coming years. No data at the moment has broken the universe, says Priyamvada Natarajan, a theoretical astrophysicist at Yale University in New Haven, Connecticut. But I think there are interesting potential tensions emerging on different scales, Natarajan said. Resolving these tensions will require researchers to revisit their fundamental assumptions about galactic evolution. That could mean bringing new ideas to the forefront while leaving others in the cosmic dustbin. But note that this is not the first time that we have spotted the too early galaxies. In May of 2009, astronauts installed one of Hubble's final and most important instruments. Known as the Wide Field Camera, or WFC-3, it vastly improved the telescope's ability to see in infrared. As the universe expands, traveling light gets stretched out to longer wavelengths, or the redder portions of the electromagnetic spectrum, so the oldest entities can't be seen in the shorter ultraviolet or visible wavelengths. WFC-3 allowed Hubble to capture the light from several record-breaking objects, including the galaxy GNZ11, which existed when our universe was only 3% of its current age, or a mere 400 million years old. Yet Hubble never found much from this early epoch. Were the few visible big bright galaxies due to limitations in the observatory's instruments? Or were astronomers witnessing the very beginnings of galaxy formation? Once JWST launched in December 2021, scientists swiftly dismissed the latter possibility. Two teams spotted the galaxy Glass Z12, about 50 million years older than GNZ11. Other JWST observations showed staggering numbers of galaxies potentially existing as early as 180 million years after the Big Bang. There's a lot of galaxies that are bright enough for us to detect with the JWST, says Jehan Karteltepe, an astrophysicist at the Rochester Institute of Technology in New York. We knew there would be some, but people were surprised at how many there are and how easy they were to find, he said. These galaxies are also potentially more massive than cosmologists expected. The scorching conditions in the first few 100,000 years after the Big Bang meant that matter couldn't settle down and condense into entities such as stars and galaxies. As the universe expanded and cooled, standard cosmological theories hold that particles of dark matter, mysterious stuff that outweighs normal matter about 6 to 1, clumped under the force of gravity and formed massive halos. These then gravitationally attracted regular matter, which slowly accumulated in the halos and produced the stars and galaxies we see today. Most models estimate that a galaxy the size of our Milky Way wouldn't form until roughly 1 to 2 billion years after the Big Bang. Yet, in that first JWST image of the SMACS 0723 cluster, astrophysicist Erica June Nelson of the University of Colorado Boulder noticed, quote, these big honking red disks, end quote, that appeared to be extremely massive galaxies rapidly forming stars. These dusty red elongated galaxies, 6 of them, all seem to have existed within the first 500 to 700 million years of cosmic history. Based on the object's brightness, Nelson's team calculated that they might each weigh at least 100 billion times the Sun's mass. One in particular was a colossus containing perhaps 100 billion suns, on par with our own galaxy, and could have 2 nearby companions, suggesting that it was part of a galactic group. Their quoted properties are so massive that it's really hard to see how you can form those and keep our current models of cosmology completely intact, says Michael Boylan-Colchin, a theoretical astrophysicist at the University of Texas at Austin. Not everyone is convinced that these objects are quite so hefty or so distant. A group of astronomers from the United States and France pointed out that the galaxy's properties suggest that they could be mostly filled with young, low-mass stars, which would make them about 1,000 times less massive than originally calculated. Nelson and her colleagues spent a good deal of time investigating this possibility in their own work, eventually dismissing it as requiring too many unlike premises to be right. Another paper from the Cosmic Evolution Early Release Science, or SEERS program, one of the major JWST survey teams, estimated that the largest galaxy is actually located much closer to us at an era more than 1 billion years after the Big Bang. By applying a set of assumptions to the same data, they posit that a fraction of its overall light could be coming from a supermassive black hole feeding on material in its center, meaning that it has fewer stars and roughly 10 times lower mass overall, an interpretation that Nelson agrees is probably correct. Such discrepancies point to the difficulty of early JWST science. Most of the telescope's initial results have been based on imaging data, in which a galaxy's distance and mass are inferred based on its brightness and color. This method is useful, but beholden to certain assumptions. To nail down an object's properties, as well as its time and place in cosmic history, astronomers typically rely on the more painstaking process of spectroscopy, in which light is separated into its constituent colors containing telltale chemical signatures. Cosmic expansion steadily shifts these signatures en masse toward longer wavelengths, providing an accurate measure of the distance light has traveled. In one instance, imaging data from JWST placed a galaxy dubbed Sears 93316 at 240 million years after the Big Bang, making it one of the most distant objects ever recorded. But about a year after that, spectroscopic measurements from the telescope showed that it was far closer, existing at a less record-breaking epoch, 1.2 billion years after the Big Bang. In other cases, spectroscopy backed up initial estimates. 4 distant galaxies spotted early on in the JWST Advanced Deep Extragalactic Survey, or JADES, were shown to be at their originally identified extreme distances. That includes JADES GSZ13-0, the current champion, which existed roughly 320 million years after the Big Bang. When the telescope's next observation cycle begins, in July, its spectrograph will deliver data on a large number of such objects, including Nelson and her colleagues' potentially massive and faraway galaxies. Still, the main galaxies that JWST has found are already enticing theorists to reconsider some of their basic ideas. Cosmological models predict the number of dark matter halos of different sizes that should be present at different epochs of the universe's history. If we say galaxies only live inside these lumps of dark matter, there aren't quite enough dark matter lumps to host the galaxies that have been reported, says Alice Shapley, an astronomer at the University of California, Los Angeles. As a result, computer simulations that produce too few dark matter halos and galaxies have fallen by the wayside. Additional data might force further modifications. People still have wiggle room surrounding the exact number and masses and formation times of galaxies, but this wiggle room is getting squeezed, says astronomer Haojin Yan of the University of Missouri in Columbia. Most in the field acknowledge that their understanding of galaxy formation will likely have to shift to account for the JWST observations. But will it be a minor adjustment or a more radical alteration? Among the simpler possibilities is that the earliest stars and galaxies came together more efficiently than researchers currently believe. It could be that the primordial universe was much denser and more compact than researchers think, perhaps allowing gas and dust to collapse especially quickly into stars. Maybe in the very earliest systems, it's all kind of going gangbusters and there's nothing to stop it, Boylan Colchin says. This would allow for the creation of a large number of galaxies that are heavier much earlier in the cosmic history than existing theories suggest. But the efficiency of galaxy formation would likely have to be much higher than current models assume. A more exotic explanation tweaks conceptions of dark energy, which is generally believed to be caused by the observed accelerated expansion of the universe. Physicists consider the density of dark energy to have been a constant since the Big Bang, but discrepant measurements of the cosmos's expansion might require a rethink of the nature of dark energy altogether. Studies of the nearby universe suggest a faster expansion rate than the rate extrapolated from observations of the infant universe. Several models that have been around since before JWST launched, called early dark energy, posit that more dark energy existed roughly 50,000 years after the Big Bang, Boylan Colchin says. Such models, which help resolve the expansion rate discrepancy, also happen to predict that galaxies grew faster and more abundantly in the early universe, which could explain the JWST sightings. But there's an obvious problem. The standard model of cosmology, with its constant dark energy density, has been extremely successful in explaining the evolution of the large-scale structure of the universe, comprising the observed web of galaxies, galactic clusters, and clusters of clusters. Any changes to that model will need to retain such positive aspects while addressing the new observations. Most researchers are taking a wait-and-see approach before abandoning long-standing ideas in favor of some new view of the cosmos. Regardless, the new eye on the sky has energized and pushed astronomers to question bedrock assumptions. As Shapley says, "You've got a few times in your career when you're like, okay, this is a watershed moment, and we're in one of those watershed moments right now." And now a question comes to our mind. Well, if the Big Bang Theory is just a theory, are there other hypothetical explanations for the origin of the known universe? Well, the short answer is yes. And here are 4 of the interesting alternatives to the Big Bang Theory. Number 1, quasi-steady-state theory. Steady-state theory can be considered as a direct contradiction to the Big Bang Theory. It suggested that the universe never had a beginning and has existed forever with a uniform density. Due to various drawbacks of this theory, it was later updated to quasi-steady-state theory. It stated that as the universe expands, there are packets of matter which are constantly being created to maintain the density of the universe. But this theory wasn't able to convince scientists as effectively as the Big Bang Theory did. The data from the CMB proved that a huge explosion had happened billions of years ago, around 14 billion years, which marked the beginning of the universe. Alternative theory number 2, mirror universe theory. The mirror universe theory is a very hypothetical yet interesting alternative model to the Big Bang Theory. It states that during the Big Bang 2 universes were born, one proceeding forward in time and the other proceeding backwards in time. It implies that the time our universe proceeds from its birth to death, but also proceeds from death to its birth in the mirror universe. The movie Tenet gives the best example of such a model, where the entropy of the objects is reversed, which makes them run backward in time. Number 3, digital simulation. Technology in the 21st century has enabled humans to develop and control a simulation of various physical aspects of our surroundings through smart computers. The advancement of technology will ensure a steady development in the domain of simulations possible by humans. Sometime in the future, there is a chance of this domain to expand and make it possible for humans to simulate a whole universe that can be controlled by using varying initial and final conditions. Want to know more about digital simulation? Check out Are We Living in a Simulation by Erickson Blogs. Yet this additionally questions our reality as a universe that is not recreated. Scientists have wondered, what if our universe is also simulated by some highly intelligent civilization, and our fates are predetermined by them? This theory of predeterminism is also supported by the concept of quantum entanglement. Here, information travels faster than the speed of light, violating the rules of the theory of relativity. One of the possible reasons for this phenomenon is predeterminism, where the spin of the entangled electrons is determined at the beginning of the universe itself. Theory number 4, multiverse theory. The theory of multiverse states that there is an infinite number of universes that are being born due to fluctuations in dark energy leading to multiple Big Bangs like explosions. Many such universes created due to the explosions cannot sustain themselves and eventually collapse to form a black hole. But some universes, like ours, had an explosion that was sufficient enough to expand itself and will continue till all the matter in the universe is separated from each other, creating a space of dark energy, wherein again the process of Big Bang happens and new universes keep on forming constantly. Apart from these alternate theories, There are many other exciting hypotheses, such as inflation theory, infinite universe theory, gravity rainbow, etc., which, though had a good base and logic but failed to beat the Big Bang theory, which is still the most widely accepted theory in the world. But the Big Bang theory is also a hypothesis that hasn't completely been proved and understood just yet, so the origin of the universe is really still a mystery to mankind. Well, that's all the information we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit that bell so you never miss out on future episodes. And be sure to tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content like this and to always improve. And as always, thanks for watching, and we'll see you next time.